So one of the things I've noticed in my Altair build is my memory cards get really warm. There's three 7805 regulators on each one of the cards, and they're grouped together, stacked next to each other, and it generates a lot of heat above the voltage regulators of that card, and there's not a lot of airflow there, and I'm afraid with the case on it's going to get very warm around them. So the question is, can I move that waste heat someplace else? So let's talk about waste heat. If we look at the schematic for the power supply we put together previously, we've got our transformer or our diode bridge. We've got the alternating DC coming out and being filtered by that very large filter cap here. And what we're getting is about 8.1 volts here with the system running. So I've got 8.1 volts coming to the input on each one of the 7805 regulators in the system. And by the way, there's 18 total in my system, but we're going to simplify the model down to just these four. So let's say if I had four regulators and each one was regulating 5 volts at 1 amp, there was a full amp of current draw, that regulator would need to take the difference between the incoming voltage and the outgoing voltage and dissipate it as heat. In this case, each regulator needs to drop 3.1 volts because there's 8.1 coming in and 5 out. And if we take that 3.1 volts and we times it by the 1 amp current, we get 3.1 watts, which is a fair amount of heat. With all those voltage regulators, they're each one of the three on each board's dissipating less than that, but they're grouped tightly together, and there's a lot of heat being generated, like I said, right at that spot. So what could we do to mitigate this? How could we move that heat to someplace else in the system? Well, one way to do this, we get into the other schematic here, is to add a dropping resistor here. Oh, excuse me. So what I'm going to do is add a 0.2 ohm resistor between the filter cap and the voltage regulators. And if you do the math here, 0.2 ohms at 5 amps current draw will drop about 1 volt across that resistor. And if we take 1 volt across that resistor at 5 amps, we dissipate 5 watts here. So we can just get rid of 5 watts of that waste heat right on this resistor. We can mount that at the back in the case, maybe near the fan, to draw the heat out, and that way the heat's not being created up in the front of the case on the the cards themselves. So what we end up here is, again, we've got the 8.1 volts here. We're immediately dropping about 1 volt across this resistor. So we have 7.1 volts now coming into the voltage regulators. And if we do the math here, 7.1 volts at 5 amps is about 10.5 watts. Remember, previously we had 15.5 watts here. Well, if we take the 10.5 and we add the 5 we're dropping over here, we're still dropping that 15.5 watts. We've just moved a third of it over to this resistor. If we come down here into the regulators, each regulator needs to drop 2.1 volts because we've got 8.1 here, about 1 volt drop gives us 7.1 here. So it's only dropping 2.1 volts, and that gives us 2.1 watts heat at each one of the regulators in this model of 4 regulators here. So we've effectively taken a third of the heat that's being generated on the boards on the S100 bus, and we're moving it out to this resistor. This isn't an uncommon thing to do. As the current changes in the system, of course, this heat will increase or decrease. That voltage will change slightly, but even at 7.1 volts coming into the regulators here, that's plenty of overhead for the regulators to get good regulation and do their thing. So I got up on DigiKey, and I did a search, and I found this resistor here. It's 0.2 ohms, it's 50 watts. It's ridiculously large for what I need, but it was $3. And I went, for $3, I can add a resistor that has mounting tabs on it so I can mount it up against sheet metal in the case. That'll help draw heat away. It's 10 times overrated for what I need to dissipate, so it's not really going to get warm. It's got plenty of surface area to dissipate that heat. And effectively we'll move, that 5 watts of heat that we're generating to get rid of voltage to someplace else in the case. In this case, it'll be in the back of the case. It'll be mounted between that large electrolytic filter cap, this guy here, and the cooling fan. Now, those will put maybe a little bit more heat near that cap, and of course, heat and electrolytic caps don't mix well. I just don't see it being a problem. So I think this is really a good compromise. I did some testing. I've got a very large passive resistive load that can be switched from 0.1 ohms up to 99.9 ohms. And I played with that load at, at 0.1 ohms, at 0.2, at 0.5, and came up with that load at 0.2 really being what I wanted. It gives me about 7.1 volts out here. It'll move the heat, as we said. So really it makes sense to me. So let's go back and look at the original sheet. Keep in mind here it's now 7.1 volts here and 2.1 volt drop. And let's just go back and review the original sheet where it's 8.1 volts into the regulator and a 3.1 volt drop. So hopefully this makes some sense. We're just going to move about a third of the heat we need to dissipate off to this resistor. It's a very large, oversized resistor. It'll deal with the heat just fine. It'll mean a bit of a wiring change in the case, but that's no big deal. So I really think this is a good solution for what I want to do. So we'll jump into the video here next, and we'll go ahead and add that resistor and give it a test. So as I look at making the mod to the power supply, the first thing I want to do is take a look at the system itself. So I've got an amp meter set up here on the amp scale and a voltmeter. We're going to measure the current being delivered to all the cards in the card cage. And the voltage is, the raw voltage being delivered as well. So if we power the system up, we can see that we're drawing 5.27 amps. And the voltage is right about 8. And as we talked about in the previous segment, the idea is to offset some voltage back to the back of the case here to dissipate the heat back here, rather than here, where all the heat sinks are on the front of the case. So let's look at making that mod next. So it took a fair amount of wrestling to get that resistor in, just because of the confined workplace. I'll tilt the case up so you can see it back in here. It's all mounted down nice and solid. It should be absolutely fine there. I'm randomly flipping switches. And now I need to feed this line through the sleeving. Hopefully I can get it to push all the way through. Kind of get these all kind of in a grab the wire tie and tie this end of this off. And this lead's going to come around to, I've actually got a tie strip here that we can use temporarily to line these up so we get a decent length. Of course, it's going to go in black, white, brown. And if I had that slid, red's going to get trimmed to about right there. Oh man, stuff is so hard to strip. I've got a crimp terminal here. My handy dandy magic crimp tool. tighter. Really don't want this crimp coming loose. That looks to have a good length. I'm happy with it. At least these, and I'm actually gonna release this wire tie because I want this slid further up. Where I set the wire ties. Come on. That should get me back to seems shorter, but it really can't be because the red lead we added has plenty of length. So really, it's time to put the card cage back in. So we're going to go ahead and measure what we've done here. I've now got 3 meters in this system. This meter is going to measure the current into the system, and it should hopefully align with what we measured before. If I can spot the piece of paper. This meter is going to measure the voltage that's coming onto the backplane, and this meter is going to measure the voltage drop across that resistor we added. So let's go ahead and apply power. And we can see that we're drawing 5.21 amps in this case. So let me write that down. So I equals, actually that's 5.18. We've got 7.1 volts. 0.15 volts to the backplane to the voltage regulators, and we've got 1.05 volts drop across that resistor we added. So I realized as I was editing the video that I didn't misspeak, but I wasn't really clear during the parts of the video where we were actually adding the resistor to the system. So I want to recap here what we did and actually show the math. So if we look at the original schematic of my power supply, we've got the transformer, the diode bridge, and the filter cap, and we're getting 8.2 volts here at the capacitor, and the system is drawing 5.27 amps. So if we take, again, that 5.27 amps and the 8.2 volts, and we multiply those together, we get the total power consumption of the system, in this case 43.22 watts. So everything is drawing 43.22 watts. If we had a perfect regulated 5 volts across all of these voltage regulators, if each one was regulating at 5 volts, and we take that 5.27 amps and we times it by that 5 volts, the electronics themselves are consuming 26.35 watts. And that means we're creating waste heat. And so if we take the 8.2 volts and minus the 5 volts we regulated out, we end up with a 3.2 volt delta. And again, if we multiply those together, we get 16.86 watts of waste heat in the system. So the idea here was to move this waste heat away from the voltage regulators on the board and someplace else in the case where it wouldn't be as troublesome. And so what we did, if you notice right here, is we added this 0.21 resistor here between the filter cap and the voltage regulators. Notice there's no resistor up here. And if we work through the math again, we get the same thing. System drawing 5.27 amps, 8.2 volts, If we multiply those together, we get the same 43.22 watts consumed. But there's a voltage drop across this resistor. The resistor's fixed. There's 5.27 amps flowing through it. If you do the math, you get 1.05 volts. So if we take the 1.05 volts across that dropping resistor, and again it is current times voltage, we get 5.54 watts waste heat right here at this resistor. If we subtract these then, we end up with 7.15 volts, and that 7.15 volts here is what's actually coming out to all the voltage regulators. Again, if we take the regulated 5 volts and we times current times voltage, we get the same 26.35 watts consumed by the electronics as we had up here. But in this case now, the voltage drop across each regulator is 2.15 volts, the 7.15 minus 5, versus the 8.2 minus 5 up here. And again, if we do the math, which is the same current draw times the 2.15 volts, we get 11.33 watts waste heat across all the voltage regulators in the system. So what we've done is essentially we've taken 5.54 watts of waste heat and we've moved it away from the regulators to the resistor, and so that means the regulators are dissipating about 1/3 less total heat. So there's now 11.33 watts waste heat spread across the regulators. The system's been running for about an hour now. If I lay my hand across the memory cards, where those 12 regulators exist, there's 3 regulators on each memory card, and there's 4 cards in the system. So there's 12 7805s just in a very tight area there. The system is much cooler there. I can actually touch the top heatsink with my finger comfortably. Versus before, those extra 5 watts, it was really uncomfortable to keep a finger on it. So, all we've really done as we started the video out is we've taken the waste heat across all these regulators, and we've moved some of that waste heat to a single resistor here. And that's a 0.2 ohm, 50 watt. We're dissipating 5.5 watts, well within spec for that resistor. So really, this is the final math on what we've done. Now, a thing to note here is because the resistance is fixed, as the current changes, the voltage drop across here is going to change. If the current's fixed and the resistance is fixed, the voltage will change. There's a relationship, Ohm's law, between voltage, current, and resistance. And if we pulled cards out and decreased the current draw, the voltage drop here would go down. No, it would go down because it would be less current. It would go down anyhow because the total current draw in the system, I said that very poorly. But as we decrease the current here, we decrease the voltage drop here. It's just reality. So, this isn't a perfect solution, but it is a way of moving heat around inside of a case. So hopefully the math here makes a bit more sense. I realized when I was talking in the assembly video that I was talking total system consumption, this 43.22 watts here, and not talking about waste heat up there. And really what we've done here, and I've probably said it 5 times now, it's just managing where the waste heat gets created in the system. Waste heat is always a reality of electronics if you have a regulated power supply. In this case, we're trying to get good 5-volt regulation across the boards. The last thing I'll say is I've looked at a number of data sheets from different manufacturers for 7805, and they all basically say the minimum input voltage is 7 volts to get good regulation. I've looked at a couple websites where people have kind of put their ideas out, and they talk about 7.5 volts, and I think that 7.5 volts maybe on older voltage regulators. But the data sheets I've looked at all call for 7 volts. The system is working very well with the 7.15 volts coming in. I'm happy with the build at this point. If I added a couple more cards, and we could actually do the math here. Let me bring up the calculator. It should be on the screen. So let's say we added 2 more cards that bump the current up to, let's just call it 7 amps. Let's take a nice 7 amps. If we take 7 amps times 0.2 ohms, we'd get 1.4 volts drop across this resistor. And if we take the 8.2 volts coming in and minus the 1.4 volts, we'd end up with 6.8 volts at the regulators, and so we might start to run into issues with the regulators not regulating well. But that again, it'd be adding 1.6 amps, actually about 1.7 amps draw to the system. You know, I don't think I'm going to add more cards in here that are actually going to have that kind of current draw. Let's do the same math for 6 amps. So if we've got 6 amps divided by 0.2 ohms, oops, let me clear here. 6 amps divide 0.2 ohms. I did something wrong there. 6 amps times 0.2 ohms, I think I hit divide. We're getting 1.2 volts drop, and if we take that 8.2 coming in, what did I do wrong here? We'd end up exactly at 7 volts. Yeah, we'd end up at 7 volts, so we would basically lower the voltage right down to about 7 volts. So I've got a bit of overhead here if I add additional current demands by plugging extra cards in. 10 of the 12 slots are filled. I can't really load the system much more. Hopefully this makes some sense. Like I say, I wanted to finish up with all the math here and, you know, all the calculations. If you don't understand Ohm's law, if you don't understand the math, just search Google Ohm's law, OHMS, Ohm's law, and it'll talk about the relationship between voltage, current, and resistance. Hopefully this wraps the video up here. Hopefully this kind of clarified at the end what we did, why we did it, and what the math shows we did. I guess with that said, I'll wrap this up and we'll talk soon.